Okay, chapter 2 is called Polynomial Power and Rational Functions, which means, again, we're going to review a lot of stuff that you did in Algebra 2, but we're going to go in a little bit deeper and do some more things that you didn't do in Algebra 2 as well. So today we're going to talk about mostly quadratic functions and linear functions, and again, there's a lot of models that do this, and so day 2 of this lesson we'll actually look at some models and how we can use technology to help us graph those, okay? So any polynomial function can be written in the form where you just have like a bunch of powers. And I didn't type this out because I wanted you to be able to see it. So any polynomial function can be written in the form f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus dot 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 plus a1x plus a0. And people kind of get really freaked out when they see stuff like this, which is why in Algebra 2 we don't show you a lot of this. But mostly polynomial functions, we normally write them with the highest degree first. That's the x to the n, and then we count down. And these are just the coefficients all the way down till you have the last number. So an example of that would be like g of x equals 4x cubed minus 3x squared plus 1, right? That's a polynomial. Really important. Where a is a real number, so polynomials have only real number coefficients, and n is a whole number. So that means to be a polynomial, you could not have fractional or decimal exponents. And then we want to make sure we talk about the leading coefficient and the degree. The degree is the highest exponent in the problem, right? So that's why we say n, normally written first, but not required. And then a sub n, the coefficient in front of the highest exponent, is the leading coefficient. So let's just practice some of that. It says determine if the function is a polynomial function. If so, state the degree and the leading coefficient. So this first one, that's just a linear function, but a linear function is a polynomial function. So yes, it's a polynomial function. The degree is the highest exponent, which in this case is just 1. And the leading coefficient, which I'm just going to shorthand here, is not -9. It's the number in front of that highest exponent, which in this case would be 2. So be careful about some of these, okay? So like, don't get tricked too much by it. Like this one, it says f of x equals 13. Some people want to say it's not a polynomial, but it really is. It's a constant function. Right? So it's the constant function like f of x equals a. So the degree of this, well, think about this, would be like 0x plus 13. Nope, just kidding. We wouldn't say 0x, would we? I don't know. I think of it like that. Like it's still like there's no x there. But the degree here is 0. There is no x. There is no x to put a power on. So I don't want to confuse you by putting the 0x there. So this would be degree 0. The leading coefficient, I want to say the leading coefficient is 13 here. Some people want to argue and say the leading coefficient is 13. 13. Some people want to say it's 0 because it's like there's no x there. But if the degree is 0, and that's with the 13, then I'm saying the leading coefficient is 13. Okay? What about this guy? If we rewrote that as an exponent, right, that's x to the -1. So having x's in the denominator of a fraction is not a polynomial function. That's a rational function. So this one is not a polynomial. Okay? Linear functions, I'm not going to talk a lot about this because I really hope that you feel good about writing linear functions. But it says write the equation for linear function such that f of -1 equals 2 and f of 2 equals 3. Well, remember that this is just function notation. That's just ordered pairs, right? This is x, and when x is -1, the y is 2. So this is like the ordered pair -1, 2, and this is the ordered pair 2, 3. Well, if it's a linear function, you should know the form of the equation that we can use, y equals mx plus b, or point slope form, y minus y1 equals m times x minus x1. You should be able to do this. So step 1 is I'm going to find my slope. So I'm going to subtract my y's on the top, and it doesn't matter which order you go as long as you go in the same direction both ways. So I'm going to go 3 minus 2, which means I'm then going to go 2 minus negative 1. So that's going to be a slope of 1/3. And then it says write an equation. It doesn't say we have to graph that equation. So you have two options. One option is you could do y equals mx plus b, where you plug in the slope and you plug in the point and you solve for b. I'm a huge fan of point slope form because one, it's already an equation, and two, it doesn't say I have to solve this out. So remember that in point slope form, this is your slope, and the x1, y1 is just a point. So you can pick either one of these points. I'll just do this one first. So if I plug in the y, so that would be y minus 2 equals my slope, which is 1/3, times x minus negative 1. And that is an equation, right? It doesn't say it has to be in slope-intercept form. So also accepted here, what if you use this point? You could say y minus 3 equals 1/3 times x minus 2, because those are both ways to represent that problem. And what's really cool about this is if you put these in slope-intercept form, they both turn out the same way. So just know, point slope form saves you some time. Okay, what we really want to focus on for this video is talking about another way to work with quadratic equations. And so the standard form of a quadratic equation is this. F of x equals ax squared plus bx plus c. That's what we use when we do the quadratic formula, right? But it can also be written in vertex form. So this is vertex form. And if you think about the transformations that we just did in chapter 1, this kind of makes sense of what happens for a quadratic. So in vertex form, you have a times the quantity x minus h squared plus k. If you have it in vertex form, then your vertex is just at hk. And a tells you whether it opens up or down, because if it's negative, it's going to open down. If it's positive, it's going to open up. And a is going to tell you if it's a stretch or a shrink also. So the big thing that we want to be able to do is put these in vertex form. So let's look at a couple examples here. So first of all, this is kind of just like what we did on the chapter 1 test. It says describe how to transform the graph and then sketch the graph. So we're going from our parent graph of f of x equals x squared to this. So right away, my vertex, I can tell here that my vertex is at hk. And be really careful, it's minus h plus k. So you always take the opposite sign of the inside. So minus 2 really means that that's just at 2. And then plus k, my vertex is 3. So think about my transformations. This graph has moved 2 to the right and up 3. And then think about the number in front. Well, it's still positive, so it's going to open up. But that number in the front is going to be like our stretch. So it's also going to be vertically stretched by a factor of 2. So if I know my normal graph, I can make a graph for this without much effort. So I know the normal x squared, and I'm going to graph that in black just like we did before. Normal x squared starts at 0, 0, 1, 1, negative 1, 1, and if I plug in 2, I get 4, right? That's what, and you don't have to graph the parent one. I just think it's helpful as I'm trying to show you the transformations. Now if I take this graph and I move it right 2 and up 3, this is now my new vertex. If I didn't stretch it by a factor of 2, I would make a point here and a point here, and I could go over 2, up 4, right? But I stretched it by a factor of 2, which means it's going to go up twice as fast. So now when I go over 1, I'm going to go up 2. And normally I go over 2, up 4. Now I'd have to go over 2, up 8. 1, 2, 3, 4, 5, 6, 7, 8. That would be like this. So what should happen is this is going to look a lot thinner than the other graph. And that would be, oh look, they both say f of x, so that's no good. Okay. I guess you really should just graph the blue one. Worst case scenario here, you can make an XY chart. And if you are making an XY chart, start with what makes that go to 0. So start with 2, because 2 makes that parenthesis go to 0, and pick one on either side of it, and you will get these 3 points, okay? But I hope that you don't have to make an XY chart every time. So you can see that having the vertex form is helpful. Okay, it says rewrite the equation in vertex form, state the vertex and the axis of symmetry. So we need to write this in vertex form, which means we need to take something that's not written as a perfect square and write it as a perfect square. And this is where we're going to complete the square. And this is where completing the square has to happen. There's not another way to do this. And this is where completing the square gets a little more complicated because we have to do this without moving stuff over. Like think about normally when we're solving an equation, the first thing I would do is add 5 over. But I can't do that with f of x. So what we do for this is we kind of group the first two together, right? The x squared plus 4x, leave a spot to complete the square, and then stick that minus 5 out to the end. So I'm just kind of separating it, kind of like the plus k out here. Then I'm going to complete the square like I've always done, which means I take half of this number and I square it. So half of 4 is 2, and 2 squared is 4. So that's what's going to make the perfect square. So I'm going to add 4 right here. Normally, when I'm solving an equation, I add 4 here, and I add 4 to this side. I can't add 4 to f of x. So you have to think about, what could I do out here on the same side of the equation that would undo this adding 4? Or think about, if you added 4 over here, what would I have to do to move it back over? And hopefully you kind of remember this from last year, that we just do the opposite, right? If I'm adding 4 inside the parentheses, I can subtract 4 outside the parentheses, and everything's the same. So I get x. I got to factor this, right? What multiplies to give me 4 that adds to give me 4? What perfect square is that going to be? It's always half of that middle number, so that factors into x plus 2 squared, and negative 5 minus 4 is negative 9. And I've taken something from standard form and moved it to vertex form. And then I want to know, what is the vertex? The vertex is HK, but remember, it's the opposite here. So if this is plus 2, that really means that it's negative 2, because that really means it's moved left 2, and negative 9. The axis of symmetry, let me go back to this graph for a minute. The axis of symmetry is that line that cuts your parabola in half. When your graph hasn't moved, that's always just the line x equals 0. But it's always just going to be, let's go back to this one. Your axis of symmetry is always just going to be x equals h when you're in vertex form. So if you know the vertex, you also know the axis of symmetry is the line through the vertex, which is x equals negative 2. I'm going to stop because I'm taking up a lot of time here. But I want you to look at the textbook at this one or at an example like this, and then we will look at it together. But the big thing about this is that there's a 2 in front of this, and we can't divide it out. So we have to factor it out. So that would give us x squared plus 3x. Leave my spot, and then still kick my negative 7 out there. Because remember, you can't complete the square unless you have nothing in front of the x squared. So we can't divide by 2 because we can't divide f of x by 2. But what I can do is factor it out. And so then go ahead and see if you can figure out what goes here. And you'll have to do the same thing out here, and we'll start there in class.